Okay, so going to look through the Core Pure 1 paper of June 2023 on the Edexcel and look at question 6. And this is a differential equation one, which has 4 parts to it. One where you set the differential equation up, and actually that's not too bad. You can get a lot worse ones than this particular one. Then one where you do a little bit of differentiating separately to the equation, but the differential equation, but you end up using the differential you do in part B. In part C, where you actually go on and solve the differential equation. And then once you've got your differential equation sorted, you then evaluate that model. So here we go. So we've got water flowing into this large tank. We know that when T equals 0, V equals 10, so right at this time there's 10 litres of water in this tank, and it tells you that the V litres in at T time, and the water enters the tank at a rate of 3 minus 4 over 1 plus e to the 0.8 T litres per minute, lovely, and then leaves the tank at a rate proportional to the volume of water remaining in the tank. And the first thing you have to do is show the volume of the water in the tank satisfies the differential equation they give you. So let's have a look at this. If we look at water in, first of all, they give us that. They tell us the water comes in at this rate, and if it's coming in at this rate, that's what dV by dt is. So dV by dt in is this 3 minus, let me have a quick look, 4 over 1 plus e to the 0.8 t. Okay, so that's the water in. But then there's water leaving this tank at a rate that is proportional to the volume of water remaining in the tank at the time. So water out is going to be dV by dt this time, just proportional to the amount of the volume of water at the moment. So it's just K times V, where K is some constant. So therefore, in total, you do V by dt is going to be water in, take away, water out. So 3 minus 4 over 1 plus e to 0.8 t minus your kV. Now, it tells us that when t equals 0, the volume of water in the tank is decreasing at a rate of 3 litres. So when t equals 0, we know dV by dt decreasing, so it's going to be minus 3. Okay? And we also know that when t equals 0, v equals 10. So I'll put that over there as well, because we're going to need that. So we're going to just plug those numbers into there specifically to work out that constant. So if we plug those numbers in there, we get minus 3 equals 3 minus 4 over 1 plus e 0.8t, so that's e to the 0, which is obviously 1, minus kv, so minus 10k. So there we have a nice little equation. We can work out what the k is. So we plug all that in and we get k is, I've done this question earlier, 0.4. Okay? And then putting that into there, we end up with exactly what they want. And showed enough steps to be able to do that, to convince them, yes, we know what we're doing there. Okay, now then, your part B. Your part B is a separate little differential they want you to determine, which is obviously going to be involved later in the question. So let me just rub this off. I'll keep that there for the second. So your part B is determine d dt of arctan e to the 0.4t. Okay, now it's only a 2 marker, so it shouldn't be too lengthy a question to do. And as usual, always have your formula booklet there in front of you, going, right, have I got any help in there? And sure enough, you will find in your formula booklet that if you differentiate arctan x it goes to 1 over 1 plus x squared. Okay? So differentiate arctan x, you go to 1 over 1 plus x squared. So that means when we differentiate arctan, it's going to be 1 over 1 plus x squared. But we've got a function here, not just t, we've got e to the 0.4t. I have no idea why I put brackets on that, but never mind. So what we're going to do is go the differential of arctan e to 0.4t is, using this from our formula booklet, 1 over 1 plus x squared, but our x is e to the 0.4t, so e to the 0.4t squared. But then, because we got not a single t here, it's some function of t, we're going to have to times by that differentiated. And that differentiated is obviously 0.4 e to the 0.4t. So e to 0.4t differentiated is that. It's a chain rule basically there, isn't it? We're doing an arctan or something, treats that something like it's just t or x or whatever, and then multiply by the differential of that function. Tidy it up a bit, and we've got, let's just keep that as 0.4, shall we? 0.4 e to 0.4t over 1 plus, now, 0.4 e to 0.4t squared, when you raise the power 2, you obviously, square, you obviously multiply the powers, so that's just going to be e to 0.8t. And that starts to become kind of very familiar, because haven't we got e to 0.28t down here? In fact, haven't we got something very familiar there going on? So have that in your head. Now, if for any reason you forgot to look in your formula booklet for any help and you haven't spotted that or anything, we could have done that. We could have done it through a long route. I'm just going to, if you don't mind, show you that very quickly, that long route. We could have gone like this. So right, if I'm differentiating some function, sometimes it helps to go, right, let y equal arctan e to 0.4t. Then we can write that therefore tan y is e to 0.4t. And then we can differentiate implicitly. So tan differentiated is sec squared y, and obviously because it's a y, we have to times by dy by dt. I don't know why I keep an x there, never mind. And then on this side, differentiate that, you get your 0.4 e to the 0.4t. And then all we've got to do is go, sec squared, tan, nice link there, dy by dt. Sec squared is 1 plus tan squared. Equals 0.4 e to 0.4t. And tan squared is e to 0.4t, tan y is e to 0.4t, so tan squared is that squared. So it's going to become dy by dt is, let me put that in first, 1 plus that squared, which is e to 0.8t, equals 0.4 e to 0.4t. That over there, you got it. You got the differential. Okay? So, we're sorted there. So that's our B done. Now, part C, let's solve that differential equation. Now, it's a first order differential equation, so let me just write it out again. dv by dt equals 3 minus 4 over 1 plus e to 0.8t minus 0.4v. So first order, you can't separate it out because we can't get the v's over there and the t's over there. And you wouldn't expect that really with a further maths differential equation. We should be thinking integrating factor. And sure enough, that's what we're going to do. We're going to get the v over this side. So we're going to get dv by dt plus 0.4v equals 3 minus 4 over 1 plus e to 0.8t. And then we go, oh, hello, integrating factor will be e to the integral of just 0.4, which is e to the 0.4t. So that's going to be our integrating factor, e to the 0.4t, but we're going to multiply this through. Now, let's multiply everything through by e to the 0.4t then. E to the 0.4t, dv by dt, plus 0.4v, e to the 0.4t, equals 3 e to 0.4t, minus 4 e to 0.4t, over 1 plus 0.8. E to the 0.8t. Hopefully you can follow all this, my really poor writing, but never mind. Okay? So, this side, don't bother thinking about it, it's literally v times the integrating factor. This side, we're integrating all of this with respect to t. And this is where our part B is going to come in. So all that with respect to t. So, first term, easy integral, because it's just integrating e to the 0.4t times by 3 obviously, but we're going to get, if you want, just write as 3 divided by 0.4, e to the 0.4t, we'll tidy that up in a second. This term, oh, that's kind of like what we got when we differentiated arctan e to 0.4t in part B. So, let me just remind myself. Shall I write it up here just to remind you what we got for part B? Well, I'm sure you've got it written down. So part B, we got that the differential of arctan e to 0.4t dt turned out to be 0.4 e to the 0.4t over 1 plus e to the 0.8t. So that is pretty much like that, except it's a slight factor out, isn't it? It's a factor of 10 out. We haven't got 4 here, we've got 0.4. Okay, so this is 10 times bigger than this. So our answer for this bit is going to be 10 arctan e to 0.4t. Lovely. But don't forget your plus c. Okay, so we now got plus c in there. Right, we want our formula, the answer to this differential equation in the form of v equals f of t. So we're going to have to divide by this e to 0.4t. But first, that's c. We're going to need to sort out that c. Well, we know when t is 0, v equals 10. So we can put those initial conditions into the equation to work out what c is. So let's put that in. 10 e to the 0 equals 3 over 0.5 is 15 over 2, e to the 0 minus 10 arctan e to the 0, which is 1, plus c. So then we can just rearrange that to get what c is, and I'll go back up to here now. So working through there, we get arctan 1 is pi over 4, because tan of pi over 4 is 1. So we get c, in this case, when we put pi over 4 in there, we're going to get 5 plus 5 pi over 2 e to the 4. No, that's wrong. What do we get c? Saving myself some time, hopefully. 5 over 2 plus 5 pi over 2. Oh, it took me some time, didn't it? Okay. So, our final equation, one last step to do first, is this is 15 over 2, e to the 0.4t minus 10 arctan e to the 0.4t plus c, which is this 5 over 2 and 5 pi over 2. Sorry, that's a bit small. Divide through by the e to 0.4t and we've got our final answer. So e to 0.4t divided by that, 15 over 2. That, well, we could actually, in fact, just do 10 arctan e to 0.4t divided by e to 0.4t. Obviously don't be daft and try and cancel them or anything stupid like, oops, apologies, but you know, anything daft like that. And then we're going to have 5 plus 5 pi over 2, which has to be times by e to the 0.4t. Done. Okay, we've got our part C. 1 second, let me just get our computer back up. Ah, there it is. Right. So, all done there. Nice 6 marks. Now, after 10 minutes, the volume of water in the tank was 8 litres. Evaluate the model in light of this information. So, we're going to have to put in t equals 10 into this formula and evaluate it, basically. So, if we put t equals 10 in there, so this is part D, t equals 10 in there, stick it all in, turn to your calculator, e to the 4 that's going to turn into, that's going to be e to the 4 plus 5 pi over 2 e to the 4. Stick it all in your calculator, careful with the arctan obviously, and you get 7.41 as an answer. That's what I got anyway. Now, we now need to evaluate that. Well, it's telling us it's 8 litres. So 7.41 is not a million miles away, but against 8 litres is quite significant, I would say. So probably the best thing to do when you're kind of going, how close is it? Is firstly evaluate how far out it is, maybe do a percentage error. So if they're saying it's 8 litres and we're getting 7.41, so that's what, 0.59 out of 8. Because sorry, 0.59 out of 7.41. Sorry, that's what it really is. And this is what the model is saying, it's 8. So we do that as a percentage. I haven't done that, but I will quickly do that. 0.59 over 7.41. About 8%. It's roughly 8% out. Now that's quite considerable. And you know, it's not huge, but it's enough to say, okay, this isn't a very good model really. It's 8% out. And I think as long as you are clear in why you're judging whether it's a good model or not, by doing something like a percentage error comparison, then they're going to give you some leeway on that. So I think really, if they won't make it too kind of middle ground. If you're looking at a nice low percentage error, then you can say, oh, that's pretty good. We're happy with that. Because there's no hard and fast rules about, you know, how far percentage out you can be. But I would certainly say under, say, 3% or so, we're pretty saying that's not a bad model. Anything above that, a little bit too far out, really. Okay? So, nice little differential equation there. A lot of horrible algebra, but hopefully that all makes sense.